This is a brief presentation on using Bayes' theorem with an example in image processing. We will look at the equation and elaborate using an example in character detection. The equation consists of four parts. 1. The probability of A given X. 2. The probability of X given A. 3. The probability of A. And 4. The probability of X. Let's begin by looking at the probability of A. We will make an example of a 4-bit image field. Here our A's are the corner symbols. In my example, the entire world of A's are these four shapes. Here I have given probabilities of occurrence for each of these shapes ranging from 10% to 40%. In this example, we will be trying to detect these four shapes. The A1s are seen 10% of the time and the A4s are seen 40%. As an example, imagine that our entire world is made of images of buried treasure chests. There are corners, but some are more common than others. The sum of the probabilities of these A's must be 100%, as I have stated that these are the only shapes that are valid. Normally, we would have more shapes, as well as the detection of invalid shapes. Now we will look at the possible X's that we could get. Since we have a 4-bit visual field, we can get 16 different possible X's. Each of our original A's can result in 16 X's. Think of this as we are trying to display one of the A's, a corner, but our display has errors which can result in an X being displayed. Each X has a different probability of being displayed. This is based on a combination of a particular A being the real source and the probability of how many errors occur. The sum of all the probabilities of these X's must also equal 100%, as we can't get anything but one of these X's. Here is a graph of the probabilities of getting any of these X's. Again, each probability is a result of the number of errors and what the original shape was. This is the probability of each individual X. The plot shows that X14 is the most likely. This makes sense as it is the same shape as A4, and A4 has a high probability of occurring. Shape X1 has the lowest probability of occurring. This also makes sense as it can only occur when there are a high number of errors for all shapes. Looking at X10, the total probability of getting an X10 is about 6.45%. This is the sum of 0.4% from A1, 1.6% from A2, 1.2% from A3, and 3.2% from A4. This is the probability considering all X and all A. The probabilities for X10, given that we know the A that it comes from, is shown below this. Now a reminder of the equation. We have the probability of A and the probability of X. Now we need the probability of getting any X given a particular A. So for the probability of X given A, we are given the A, so we have 16 different possible X's. The sum of these probabilities must equal 100%. Here is a plot of the different distributions of the probabilities of X given A for all the four A's. So for the final term, given that we actually see an X, we want to calculate the probability that it came from an A1, A2, A3, or A4. This is the form of the equation. Again, the sum of these probabilities must equal 100%. In conclusion, here is the equation with some added graphical representation. The probability of A is the individual rate of occurrence of our corners in the observed world. The probability of X is the probability of seeing a given shape on our display. The probability of X given A is the probability that a certain actual corner shape will result in the error X. The probability of A given X is the probability that the displayed shape X was actually caused by a given A. Check out our Kickstarter project, A Wearable Visual Aid.